Hello again. Tonight we're going to talk about whether faster than light propulsion, FTL, is needed yet, or is there more we can do before we get there? So, faster than light is faster than the speed of light. The speed of light is very fast, and going multiple times faster than that is a big number. And then you say, well, that's just per second. Well, how far would it be if I went at that speed or faster for longer periods of time, upwards of, let's say, I don't know, decades, 10 plus years? The numbers get very, very large very quickly. As usual, I'll present both the metric and the US measurement units. It would be typical in a scientific presentation to use scientific notation, n times 10 to the m, but that kind of obscures the relative visual scale to see, well, that number has gotten very much bigger. In this particular instance, I'll avoid the scientific notation and just present with all the digits. So here's faster than light, or as they refer to it, superluminal, as in faster than light. If you really want to get somewhere in a hurry, if you're not going to do, warp drives and space bubbles and things like that, then you need to go not just the speed of light, you need to go numerous times the speed of light because the distances are so far. And we'll get to the distances on the next slide, but the Earth time units are in the left column. And then if you traveled at the speed of light, not multiple times, not FTL, but just c, traveled at that speed for that amount of time, this is how far you would go. Seconds, that's the normal speed of light, is that many kilometers or miles per second. How far you would get in 1 hour based upon 3,600 seconds per hour. Per day, roughly 24 hours in a day. Then how far in a year? And then if you remember, the New Horizons probe left Earth and traveled for 10 years to do a flyby of Pluto. And we said, well, that was okay. So if you could travel at the speed of light and you were tolerant enough to travel for 10 years, how far would you get? Comparing the speed versus distances, at what point does the distance get to be so far that you would like to consider light speed or faster because you don't have the patience, or it would just take, multiple hundreds to thousands of years, generations to get you there? So if you're going to the moon, we can get there pretty quickly. And it's a very, very tiny fraction of the speed of light. Mars and Jupiter and Saturn and even Pluto are still small fractions of the speed of light. The KBO refers to Kuiper Belt object, as opposed to me labeling things as planets or not, dwarf planets or not. And then the Oort Cloud, that's the sort of spherical cloud of leftover remnants from the formation of the solar system that forms a very low density cloud of objects of varying sizes on the outer edge of our solar system. But then going beyond our solar system, there is Proxima Centauri. That's a star in the Centaurus star system, which is closest to Earth, and that's 4.2 light years. But you can see the giant jump from, let's say, Sedna to Proxima Centauri. You can see how many kilometers or miles difference that is. It's considerable. And you say, well, I remember the movie Contact, they went to Vega. So how would it be to go to Vega? That's about 25 light years. And when you measure miles and kilometers, the numbers just get to be, as the saying goes, astronomical. So if you want to go to the outer part of the Oort Cloud or Proxima Centauri or Alpha Lyrae, you probably need some very advanced new form of propulsion that might be faster than light. But to just putter around the solar system, you don't need light speed, you need just better speed. So these are the fastest things that humans have thrown into space and the entirety of the space programs across the Earth. So the first fastest thing was when the Soviet Union sent their Luna 2 impactor, as in they launched it from Earth, and it went kind of like the early Explorer craft that we sent to the moon, where they don't have the ability to slow down. So they just keep taking images as fast as they can, and then eventually it crashes into the moon. So to get from the Earth to the moon, Luna 2 took 2 days, 14 hours, 22 minutes, 41 seconds. The escape velocity for Earth is about 25,000 miles, or a very, very small fraction of c. Luna 2 was going just fast enough to get to the moon. We can now get to the moon a little bit faster than that, but not by much. Still takes a day and a half to 2 days, depending upon the orbital distance. If you want to get from Earth to Mars, the fastest thing we've had is Mars 2020, which is the Perseverance and Ingenuity rover and helicopter. And that took 204 days, or about 7 months. And it went at, if you count the average speed throughout its travel, it was 24,600. So it left Earth at escape velocity and then got a little bit slower and then slowed for orbital insertion because it wanted to use rockets to land on Mars. The next faster thing was New Horizons to go to Pluto. This was the saying goes, biggest bada boom rocket at the time that we could launch. It was, I think, an Atlas V with all the solid boosters on it and such. It made it faster than the 25,000 miles an hour. It left Earth orbit at 36,400, still a very tiny fraction of the speed of light. The fastest thing we've ever had is the Parker Solar Probe. It has very elongated orbits around the sun. This allows it to get into lower and lower altitude orbits as it goes around the sun. It actually has an elongated orbit that has to worry about where Mercury and Venus are, because it uses Venus for gravity assists, and then it points itself towards the sun and uses the sun to accelerate itself. And between Venus and the sun, and it taking about 7 years to get going this fast, it did a flyby of the sun at 430,000 miles per hour, which is still, we shaved off 1 decimal digit from the fraction of the speed of light. That is the fastest thing that humans have put into space, and it's still a minuscule fraction of the speed of light. So do we need faster than light right now? I don't think so. What we need is significantly faster. Our chemical propulsion will allow us to get to the moon in a couple of days, and that seems to be tolerable. We can get out to Mars in about 7 months, which is okay for uncrewed probes, no human carrying capsules. If you're willing to wait a few years, like maybe as many as 10 years, we can wait for things to get to the outer planets in the solar system. But if you want to get out to the Oort Cloud, it takes a lot more patience. Chemical propulsion will only allow you to leave Earth so fast, and then it runs out of fuel, and the rest of it's essentially coasting, which is why Pluto was a flyby, because it didn't have enough fuel to slow itself down enough to go into orbit. If you want to just putter around the solar system, traveling at the speed of light or faster than light is kind of overkill. A lot of effort, a lot of money, a lot of new technology has to be developed. Let's say you just wanted to get to Sedna, which is the largest of the Kuiper Belt objects, not even in the Oort Cloud, just in the Kuiper Belt. It's well out beyond Pluto. It would take 10 years if you were traveling at 108,374 miles per hour, which is slower than the Parker Solar Probe. So if you wanted to give it 10 years, we've got to be going faster, but not as fast as Parker. So you might be able to do a slingshot a couple of times around Jupiter and Saturn to get out there faster. But you'd like to slow down. The reason why I'd like to slow down is learn from the New Horizons flyby mistake. If you do a flyby and you're not going to be next to anything interesting for a number of years or maybe decades, your budget for operational continuance is exposed, and people can say, well, we're not getting anything out of it. It's going to be way after the next election cycle, which I might lose, and therefore I'm going to remove it from the budget to be a good budget conscious individual. And so that's what happened with New Horizon. Is its budget came into question because it's not going to be near something interesting for maybe another 5 to 10 years. So I would say, whatever you're going to do, if you're going to get to Sedna, do slow down for orbital insertion, maybe take a little longer to get there, go, slow down slowly, maybe use reverse thrust ion propulsion. It might take you a couple of years to slow down, but let's say it takes you 10 years to get to Sedna. Once you're in orbit and making observations, it becomes much more difficult to cut your funding because you can show pictures. I'd say go into a polar circular orbit about Sedna, and on the left there you see a view of what that would be. Sedna would rotate underneath the orbit, and you would be going into a polar orbit around it. So between the rotation and the orbit, you can get a pole-to-pole view of Sedna and scan the whole planet, the whole object, and then send that data back to Earth. We don't know right now whether Sedna has any moons, Trojan asteroids, or ring structure because it's just too far away. So we might be able to do observations of Sedna several years before we actually get there. This is an interesting concept that I encountered many years ago, which is how long will it take you to develop the faster than light travel? 10 years, 20 years, 50 years? Okay. If you were to launch something now at the fastest possible speed you could, how long would it take to get to your destination? Let's say it's Sedna. If it took 10 years to get there and it only took 8 years to develop faster than light travel, then you could catch up with the probe before the probe got to Sedna. Or let's say you wanted a farther off target. You said, how about we go fast enough where it only takes us 20 years to get to Proxima Centauri? And then you develop faster than light travel, and now you're traveling at like 4 times the speed of light. You can catch up with the probe before it gets there, get the data from the probe, and you can either latch on to the probe and drag it along at its lower speed, or you could just say, well, I'll let it go as fast as it can go, and I'm going to go ahead and get to Proxima Centauri, and the old probe can catch up later. I definitely think it makes sense to do faster than light propulsion technology, but let's not wait until we have it. Maybe expand our puttering around capability so we can travel more often in the solar system and further out into the solar system, even though it might take some number of years. So we have 2 things we want to do at the same time: walk and chew bubblegum. So you have to balance where the money goes. If you know enough about the Artemis Accords, this is an international agreement where you've got multiple nations participating with their resources and technologies, developing different parts of the return to the moon, landing on the moon, staying on the moon kind of thing. So maybe they need to have a FTL Accords. Different countries provide different capabilities in order for us to collectively, as a species, get to FTL faster. But in the interim, let's find new ways to go faster, but nowhere near the speed of light or faster than light. Let's think of things that don't require a fixed size fuel tank. You know, the fixed size fuel tanks, whether they're liquid or solid, don't last for more than a few minutes. You want something that the propulsion can last for maybe multiple decades. Probably not going to be chemical, probably not even going to be ion propulsion. Probably don't want something that's going to require heavy shielding to avoid your electronics or your human habitants getting irradiated. So probably not what we think of as fission, fusion, or even antimatter. We need something that runs on electrons as the fuel. Easy to acquire, essentially unlimited. If you're close enough to a star, then you can use solar cells, photovoltaics. If you're a little farther out, you can use radioisotope thermoelectric generators. And sure, you can use plutonium. Even longer lasting is if you use americium. And then someday we might do some variant of the Casimir effect, and that would work not only longer, but also where starlight isn't available to run solar cells. And then we finally get to, let's do photons to electrons to photons, and then propulsion by optimized reflection of the photons. And when you do that, you essentially abstract fuel generation from fuel consumption. They're not directly coupled. Like, I can only go as far as the fixed size tank. If you can create the electrons from an open-ended source, now you have an open-ended fuel source. Something that people don't realize about ion propulsion is that on those long distance runs where the ion engine is on for many months to a year plus, it's not running at full propulsion. It's running at maybe 10 to 15% of its total, because if it ran at its full thrust level, it would run out of its fixed tank of noble gas, be it argon or krypton or xenon. It would run out of that in a matter of hours. So they have to really throttle it back, but they can leave the rocket running and add more velocity over a long period of time. So you want that ability. You want to be able to run at maximum output for a long period of time. And by moving away from ion to something that uses photons and electrons, you get rid of all the pumps and the valves and the pipes and the heaters and makes it simpler, lower cost, lighter weight, that kind of thing. But you knew I'd eventually get to radiation reflection pressure, but not solar sails, because those won't work out as far as the Kuiper Belt or the Oort Cloud or between stars. So in summary, do we need faster than light travel? In a word, no, at least not yet. Eventually someday, but not yet. There's an enormous velocity gap between our current top speed and the speed of light, let alone multiple times the speed of light. There's lots of places in the solar system we're going considerably faster, but nowhere near C would be very useful. So as long as we don't mind launching artificial intelligent robots, if it takes 10 years to get to somewhere, that's fine. If it takes 20 years, there probably won't be the political funding patience for it. But we did that with New Horizons. It took 10 years to get there, and we were patient enough for that. And when you're sending humans to distant places in the solar system, getting there faster makes sense, because otherwise you have to feed the humans, give them oxygen, things like that. So instead of creating some form of suspended animation, if you go faster, you have less need for it. So let's say you did develop a faster than light drive. What would be a meaningful multiple of C that would make your FTL drive worth it? About 20 times. If you think about, let's say, the distance to Vega, and if you're going at the speed of light, it would still take you 25 years to get there. But if you were going 20 times the speed of light, now you're talking about a velocity that will get you there in a reasonable amount of time. We have plenty of time to figure out how to do a sufficiently fast FTL drive. Maybe by then we'll be doing warp drives and the whole point will become moot. But in the interim, let's develop newer, faster, slower than the speed of light offerings, launch some stuff. And I would say focus your efforts on radiation reflection pressure. And then, as usual, lots of links. Okay.
I've got a thought from a
Yes.
philosophical human factors point of view.
Sure.
If somebody wanted to go to a place that's far away and they're going to go at the speed of light or almost the speed of light, they'd have to be going for their sake, not the people that he leaves behind, because he's leaving them way far behind in time and distance.
Yes.
And as he's going faster and faster towards the speed of light, he's really cranking out the miles, but his internal clock is slowing down.
Yes, relativistic effects. As you approach the speed of light, and certainly as you go faster than the speed of light, essentially time slows down relative to normal time. So the twin brothers paradox of Einstein, where you had one twin stay on Earth and another twin went at 3/4 the speed of light out to some distance, turned around and came back, he would still be relatively young, but his twin brother would either have passed away decades ago or be very, very old.
So thinking that he's got a mission to go to a place that's far away,
yes,
and he's getting closer and closer to the speed of light, and his clock is slowing down and slowing down, bang, he'd be there before he knows it. He's not wasting 100 years because his clock is slowed down.
No, actually, his clock would be slower, but given the vast distance, it would still take him that amount of time to get there. But from where he came from, it would not be that amount of time. It would be many times that amount of time.
Yeah.
So if you said, I'm just going to go, half a light year out to the Oort Cloud, the inner side of the Oort Cloud, fine. You could go there and get there from your perspective in a half a year and then come back in a year. So for you, 2 years. But for people on Earth, I don't have math calculated. It might be 50 years.
So it's.
But I thought that it still is going to take you less time, even from your own perspective, like Joe's saying, if I understand. Because if a photon is traveling at the speed of light, then from its own perspective, it leaves somewhere and arrives. It starts at the Big Bang and arrives on your bottom instantaneously. It doesn't know that there have been 14 billion
Right.
years. Right.
The same with an astronaut who's going at the speed of light, or his clock is slowed down to almost nothing. And even though he's passed an awful lot of miles, he doesn't feel that time. He's where he wants to be.
I have some information that might counter that, which is GPS satellites. The atomic clocks on GPS satellites still click at the expected rate, but the signal that makes it down from the satellites is dilated by the speed that they're orbiting the Earth. So internally, the clock is still clicking at the expected rate. So time local within the satellite still passes at the expected rate. But for us, it passes differently because the satellite's moving at 20 some odd thousand miles an hour. So yeah, I think that the guy traveling at half the speed of light, he will still perceive that if he goes half a light year out at half the speed of light, then he still perceives a half a year has transpired for him. But on Earth, it might be 50 years.
Yeah.
So I think time for the traveler still functions at the rate that is perceived.
Yeah, he feels regular, normal time.
Yes, he doesn't feel faster time and he doesn't feel slower time. He feels normal time.
Right. But he gets to where he wants to go awful fast because
yes, he does. But not faster. Not faster.
Well, how do they handle the frequent flyer miles?
I don't know what's above platinum. You have an unobtainium level.
What did Mel Brooks call it? He when they go faster and faster and faster, he had different labels for that.
Okay. There's ludicrous speed.
Yeah, that's right. Yeah.
Yes. And then when you go beyond ludicrous speed, there is plaid.
Yeah.
And as a joke, when Tesla first started making their Model S and they wanted to make a faster version of it, they tweaked the software and the electronic circuits and the coils on the motors. They came up with, you could set it on the display, ludicrous speed. And then they found a way to make it go even faster. And they said, what do we call this? Well, it's obvious. Plaid. So on the rear of the vehicle, it wouldn't say the word plaid. It would just have a little badge that was that glowing like light beams that you saw in the Mel Brooks movie. And you would know that person's driving a plaid.
Yeah. So engineers can have a sense of humor.
Yes. And they did the same thing to the Model Y and the Model 3. And it just became ludicrous for them to put a plaid badge on the cheapest car they had because it was not going as fast as the Model S or the Model Y in its highest speed mode. So they just called it high performance. But still, the next generation of the Tesla Roadster is supposed to go even faster than that. It will start out as an optimized plaid, and they plan on having an option that you can buy into where it will also have compressed nitrogen gas jets pointing out the back. So you could go from ludicrous to plaid to, I don't know what they're going to call it, SpaceX speed. You would no longer rely upon wheel friction on the asphalt to go faster, which is what's holding them back right now. They can only go as fast as the rubber contact with the asphalt and the resistance of the rubber to the asphalt causing the wheels to turn, meaning it moves the vehicle forward. The next fastest thing beyond that is gas propulsion. So you would have kind of like a rocket that didn't need rocket fuel because it could take the air and take the nitrogen out of it and compress it in the tanks.
Or you could feed it cabbage. That would give it plenty of gas.
Yes, but that would be methane and you wouldn't want to light it. No, I think that eventually someday you'll find vehicles that suspend themselves vertically with radiation reflection pressure and then motivate themselves forward, not by wheels on asphalt, but by radiation reflection pressure. And you won't see anything coming out the back. You won't see anything coming out the bottom, but the top side and the front side would glow dark blue because that's the shortest wavelength for reflection that still works with typical optics. You can get shorter wavelengths that will give you more momentum, but now you're talking about, well, you can't use glass. You've got to use metal for your mirrors. And then when you get up to the X-ray level, you get even more momentum out of it. But now your mirrors aren't really mirrors, they're electromagnets, kind of like the X-ray, kind of like the electromagnetic coils of an old style CRT tube or an X-ray machine.
Well, the inertia problems must be unsolvable, to try
Well,
to.
that's something that might be solved in software. They already think about that when the Tesla vehicles are moving. They're accelerating rapidly. They're in like drag strip mode, because if you make the G-force too high, you'll break the contact between the wheels and the asphalt and you'll skid. So they literally monitor the wheel spin. I think it's a couple hundred times a second. And if the wheel spin ever exceeds what they believe the forward momentum wheel rotation to be, they'll actually slow the wheel down a little bit by not giving it as much power, not by breaking it, not by applying a resistive force to it, but just not giving it as much juice.
Yeah,
So,
airplanes have that same problem. When they come in for a landing, they start spinning the wheels.
yes, yes. When you have giant airplanes, they noted that if you spin the wheels at the same speed as you'll be traveling down the runway when you first make contact, that could reduce the wear on the rubber. But then they found out the cost for sustaining that motor mechanism made the plane heavy and added more complexity, which increased the problems, the mean time between failure. So nowadays they don't do a lot of wheel spin anymore. They just take it on the nose. The tires take the brunt of the force and they make better tires.
I didn't realize they gave up on that.
Yeah, the mechanisms added weight and cost, and that becomes something that the company making the aircraft has to burden themselves with. But if it's just replacing the tires with more expensive ones or more often, that's the airline's problem.
Yeah, those shuttle tires they have to change them every time.
Yes, and those did not use wheel spin.
Yeah, yeah. So 130 shuttle missions. Imagine all the tires,
Yeah, well, there were fewer tires on the shuttle than there are on a 747. But I think the Antonov has the largest number of tires for a single aircraft. And then the Galaxy C5 is kind of in between, more than a 747, but less than an Antonov. I'm sure there's many millions of dollars per year in tire revenue based upon how many tires will the airplane need? Oh, I don't know, lots and lots of them. Okay. Any other comments or questions before I stop recording? Hearing nothing.